Hello students, good day to all. So in this video we are going to discuss about the PN junction diode, energy diagram and biasing conditions. We have a forward bias and reverse bias condition. During that part, forward bias, reverse bias condition, how the PN junction diode is working. So this topic is coming under the principles of electronics engineering. Before entering into that, we will discuss about the energy band theory and Fermi levels. So easily we know that we have two energy band. One is conduction valence band. Valence band is the bottom band, and once you are getting the energy, it will be going to the conduction band. Between these two bands, valence band and conduction band, it is separated by energy gap, that is forbidden gap. Absolute zero valence band are full, those conduction band are empty. All electrons have no energy at 0 Kelvin. Maximum energy that electrons may possess at 0 Kelvin, that is in Fermi level. So this is a conduction band and valence band we can observe for three type of materials, which is insulator, not going to conduct anything, conductors conducting fully, semiconductor is semi conduction will be happening. So here we are discussing about semiconductor, valence band and energy band, energy Fermi levels also. With that, just we are going to discuss about insulator and conductor electrical properties. So this is the insulator, the energy diagram for the insulator. Here the valence band and conduction band. Once the valence band, electrons, atoms or electrons will be getting energy, it will be moving to the conduction band. Here the gap is more, it will be around 5 electron volt. Here if you are going for a semiconductor, which we are dealing, valence band and conduction band, so the here the energy level is almost 1.1 electron volt we can have commonly. And if you are going for a conductor, this is fully conduction, there is no energy gap between these two, almost this is overlapping. We have two types of semiconductor. It is classified into two: intrinsic semiconductor, extrinsic semiconductor. Intrinsic semiconductor is pure form of semiconductor. We are not adding any impurities here. Why we are adding that impurity? So we have atoms and all, and atoms will be having electrons and holes that will be not balanced. I think it is completely balanced in the pure semiconductor. So in eccentric semiconductor, just we are adding some impurity, it will be unbalancing. First we will discuss about the intrinsic semiconductor. Here this is a valence and the conduction band. Here the once we are inducing a particular electron will be moving from valence band to conduction band. Here the intrinsic semiconductor, so we may not have the possibility once we are adding the impurity. Here this will be one will be moving, the electrons will be moving to the conduction band, so that is a conduction level, which means it will be making a hole, that is a empty, that empty will be the holes. At room temperature, some of valence electrons may acquire sufficient energy to enter into the conduction band. Here we may have the sufficient energy to enter into the conduction band. Here the electric field is applied. These free electrons, if it is moving from valence band to conduction band, it will be the electric current. So we know that the movement of free electrons is equal to the electric current. Here the missing of electrons in the valence band, here it will be missing, that will be the holes. So if the electrons are moving here to there, which means the holes will be moving there to here, that we have to assume. So in an intrinsic semiconductor, so the densities we can analyze, and also the carrier concentration. If you are going for any densities intrinsic, because it is a balance I told. So here if you are taking electrons and holes that are equal, so the carrier concentration Ni is equal to Bt 3 power 2 exponential of minus Eg divided by 2 into kT. Let we discuss about what are the terms we have, and the total electrons in the particular intrinsic semiconductor, total current we can analyze. This is not only for the electrons, because you have to take for free electrons as well as holes. So next then we can have that particular Carrier concentration, Na is equal to this term. Here B is a coefficient, Eg is your the band gap energy, and then T is a temperature, K is a Boltzmann constant, which we are taking as a constant value of 86 into 10 power minus 6. We can have this unit. So this is your we can calculate the whole term for calculating the current. So next, the second classification is extrinsic semiconductor. Extrinsic semiconductor, this is not a pure form, which we are adding the impurity. By adding the impurity, that will be the balancing. We know densities are equal, but here the density is not equal because we are adding one hole or one electrons additionally according to that in p-type and n-type semiconductor. So the concentration can be greatly increased by adding a small amount of certain impurities to intrinsic. If it is adding a density of n, that is n-type. If you are adding the density of positive, that is holes, that will be the p-type. We'll discuss about n-type semiconductor. So this is the energy band diagram. Here the holes can be created, that holes can be moved into the conduction. Now we can analyze. So here the more number of the carriers, majority carriers are there, which means if I am adding, this is a silicon semiconductor. Here this is a valence electron, that will be the antimony impurity, and is added. This is a pentavalent, antimony impurity is added, which means each and every is having only 4 electrons surround that, right? Here we have the 4 electrons and also additional fifth. This will be making unbalancing condition. This electrons, it will be creating, and the whole will be the majority carriers. That's why we are having the n-type semiconductor material. The electrons are majority carriers. Next, the p-type semiconductor. Here we had in the initially we had n-type semiconductor. Excess of one electron was there. Here one, that electron has been removed. Here this is the boron impurity, and here one electrons has been removed. Because of the remove of electrons, it will be making as a whole. Now here the holes are making the unbalancing condition, it will be creating as majority carrier. That's why in p-type semiconductor material we can have more number of holes can be produced. Next to the diode condition, in this way only the current is passing. Now this is a movement. Here one electrons are move, here one electrons will be moving in the particular, this is a movement of current direction. If it is going continuously, then we can create as a current. So this is absorbed by the, here the electrons are moving there, which will be absorbed by this positive. Now here one electrons are moving here, this is a movement of electrons in each and every way. Now we are going for the diode operating conditions. Diode operating conditions, we have three biasing. First, we are not giving any biasing, that is no biasing, forward biasing and reverse biasing. First, we will discuss about there is no biasing in the diode operation conditions. I'm having this, I'm not giving any supply, which means that is a no biasing. Because of this, there is no amount of voltage is there. Because of no voltage, there is no amount of current is there. No external voltage is applied, so the current is equal to 0. So we have the depletion layer region. The depletion region is in between p-type semiconductor and n-type semiconductor. Whatever it is designed, that will be having the p-type semiconductor, it is not having any impact. Next is a forward biasing condition. The forward biasing condition, the diode operating condition is the first one is a forward biasing. Here this is a normal level and I am giving the forward. First we know that what is forward biasing condition. Positive supply is positive DC supply and it is given to the p-type p region, and also negative is given to n-type. So that is a p-type semiconductor, and n-type semiconductor which will be receiving the same polarity, that is a forward biasing condition. By applying these conditions, it will be creating a own impact. So the resistance here we are using, that is for limiting the current, it will not be damaging the device. For that purpose only we are using that. Now after applying this, so this is a all electrons will be attracted by, here this is a majority carriers are holes and n majority carriers are. Now this is positive, we have negative we have negative, all electrons will be repelled and it will be moving, which means the majority carriers diffusing in the next one. So this all holes will be attracted by this, all electrons will be attracted. Now the diffusion will be happening, which means the charges will be moving here to there, here to there without any the disturbance. Now it will be having that impact. Now we will be discussing and we will be comparing about that important thing about the depletion layer. Normally we have the depletion layer after giving the forward, because the electrons will be moving here to there. So the large amount of current transaction and carrier the current will be moving in there, so which means it will be making as a whole impact. So that impact will be creating the less amount or that narrow depletion layer, which means, so because of the movement of the electrons or majority charge carriers, the depletion layer may be reduced. Next is will be discussing about that in between we can have the barrier potential. That barrier potential will be lesser in the forward bias, because the depletion layer is that will be narrowed when compared to the no biasing condition. Now here we can assume that we can have each and every property will be each and every material and will be having the own resistance. We can assume that Rp is a P type and Rn is your N type uh, resistance. In between we can have the barrier potential. Now whenever we can have that greater amount of barrier potential when compared to the applied voltage, it is increased at that time we can have, which means what amount of that semiconductor will be having. So we will not be having the conduction below 0.7 for silicon, below 0.7 for germanium, which means whenever we are getting 0. If I'm taking for example silicon 0.7, after 0.7 only the conduction will be, the current will be more, so it will be reflected in the VI characteristics. In reverse bias, whatever we have informed and we have explained, that we have discussed, that will be the reverse opposite, which means the depletion layer is broadened, because here the positive is connected to N region, negative is connected to P region. So here the positive, immediately the electrons will be attracted by this positive, so the electrons moving in this way. Last we can have the cross, uh, that it will be crossing the regions, but it will be away from the region, which means the depletion layer will be playing a major role. So all that non-attracted that ions, that charges will be accumulated here, which means, which impacts the depletion layer region will be having more. Because of this, the reverse voltage will be happening. Because of the reverse voltage, that reverse voltage is reverse breakdown voltage. Here the reverse breakdown voltage will be having that very high resistance, and also it depends on the very high, so the no current is flowing through the particular regions, because so that will be no crossover here, the diffusion will not be happening, the ions will be moving away. So that movement we can say that is a minority charge carriers movement. Next, we will be having that reverse saturation current. It will be having the reverse saturation current. So whatever we have 0.7, whenever it is crossing 0.7, the current will be happening. In the reverse saturation also will be having the current, because the movement of minority charge carriers, that will be in terms of microamps. So this is a main thing just we have to and also that abnormal current will be happening in the reverse bias condition. If I'm increasing the level after having the knee voltage, that amount of voltage 0.7, that will be the knee voltage. After reaching the knee voltage, the reverse bias is increased further, the current through the junction increases abruptly. That current will be the damaging current, so that will be the leakage current we can say. So that current, because of this, so we can have that voltage, that is reverse breakdown voltage. After reverse breakdown voltage only, that abnormal current will be passing there. So this by using this concept we will be discussing about VA characteristics of PN junction. So here zero biasing, forward biasing, reverse biasing. First We'll discuss about that forward biasing, the characteristics. If I'm increasing the forward bias, this is given forward bias, voltage and current. So current can be obtained against voltage. Now the voltage is varied after some value. Here we are using silicon. So after knee voltage, that is 0.7, the current is going abruptly. So next, for the same, this is just experimental arrangement for our reference only. And here the reverse bias condition, here that the connection is given in the opposite. The negative should be given to positive, and the cathode should be given into anode should be given to negative, and cathode should be positive. Cathode should be positive. So because of this, the reverse current will be there. Now we are increasing the reverse voltage. After getting the reverse breakdown voltage, it currents going abruptly. And here this is a complete VA characteristics we can have. This is a forward bias condition we'll be having, and the reverse bias also. So this is a barrier potential we have. This is knee voltage because of reverse breakdown voltage. So if in the next video we will discuss about the importance of that current that the application, which means the rectifier, for full wave rectifier and also half wave rectifier. Thank you all.